situation is not that good at the moment. So, hopefully in the future. So the title of my talk is Complex Langevin for Complex Actions, Recent Developments. So let me start with motivation. So why do we want to study models with complex actions using complex Langevin dynamics? So the main motivation is the phase diagram of QCD. So QCD phase diagram, it is not perturbative. So so there are several phases here. On the x-axis, we have the baryon chemical potential, and on the y-axis, we have temperature. And on this diagram, on this two-dimensional surface, we have several phases. Okay, several interesting phases, and some of our colleagues at TIFR, they are also exploring these theories on using lattice methods, QCD phase diagram. So the question is non-perturbative determination of QCD phase diagram. Is it possible? So at low temperature and chemical potential, QCD is confining. We know that. So maybe we could use lattice QCD. So the techniques of lattice QCD. So at zero chemical potential and finite temperature, lattice QCD works well. So we all know that lattice QCD is based on importance sampling. So the method used is Markov chain Monte Carlo. When the chemical potential is non-zero, importance sampling breaks down. Okay, so let's see how that happens. Lattice QCD is based on path integral Monte Carlo. So let's consider the field theory partition function, which is given by this. So we have the fermions denoted as psi bar and psi, then the gauge field or the link field. Then we can integrate over the fermions, and we get a determinant of a matrix. Okay, it's a fermion operator. And if this term e power minus SB, SB is the bosonic action, it contains only gluonic variables, times determinant of M, it can be interpreted as a probability weight if it is greater than zero. So if it is less than zero, or if it's complex, then it is problematic. Importance sampling doesn't work. So we can evaluate this integral using importance sampling, assuming that this object is greater than zero. But for QCD at finite baryon or quark chemical potential, the fermion determinant is complex. Okay, it has this property, and this thing is complex. So that means this theory has a sign problem. Okay, so to be more accurate, we should say that it has a complex phase problem. Okay, so when the determinant is complex, importance sampling is not possible. It breaks down. So let's express the determinant in this way, in the polar decomposition, okay, with a phase e power I phi. Then the apparent solution to this complex phase problem is we can absorb this phase into the observable, okay, phase reweighting. So we can write the expectation value of an observable in this way. So we, on the numerator, we have this observable inserted into the expression for the partition function. Then we do this polar decomposition, and we take the ratio, okay, with this phase appearing in the picture. So let's look at this phase, the expectation value of the phase. So here PQ means phase quenched, okay, when we do simulations with only the magnitude of this determinant. So that is why it's called phase quenched. So if you look at this, the phase can be written as the ratio of two partition functions. Okay, one is Z full, the full theory, and in the denominator we have Z phase quenched. Okay, and it goes like exponential of minus omega times the free energy density difference. Okay, so delta F is the difference in free energy densities. Then omega is the space-time volume. Okay, and it goes like this, the ratio. And Z full has this form, and this phase quench has this form. So the problem is when we take the thermodynamic limit, okay, this phase factor, it goes to zero if F not equal to F phase quench. Okay, that is rarely the case. So the ratio which gives this observable, it is not well defined. Okay, numerator and denominator, they vanish exponentially as omega is increased, as the lattice volume is increased. So there is an exponential dependence on the volume, lattice volume. So that means sign problem is exponentially hard. Okay, so it is difficult Now, what do we do? Is there a way around this? So one method is complex Langevin. Okay, use complex Langevin dynamics. So now, what is complex Langevin method? So this is a method that does not use important sampling. Okay, so we start with complexifying all degrees of freedom. So take phi as a field. It's a real field initially, and we complexify this. Okay, so phi goes to phi real plus I phi imaginary. So we are enlarging the space we have. Okay, so that we can move around. Okay, in the space. So we have an enlarged complexified field space. So on this complexified space, we can use either complex Langevin or Lefschetz thimbles. Okay, so there are two, almost identical methods. One is based on complex Langevin equation, and the other is deforming the contour in a certain way on the complex plane. And these contours are called Lefschetz thimbles, and we can do Monte Carlo on Lefschetz thimbles. Okay, with complex action. So we'll be focusing on complex Langevin method. So complex Langevin method, it is analogous to Brownian motion. Okay? It was first introduced by Parisi and Wu in 1981. So the idea is similar to a particle in a fluid. Okay? It experiences friction and a kick. Okay? Then we can write on the Langevin equation to describe the dynamics of this particle. So it contains the friction term and the noise or the kick. Okay? And the noise satisfies this particular constraint. Now, the solution of this equation, so the solutions appear as stochastic processes. Okay, so we can generalize this process by introducing another variable y. Okay, and call z equal to x plus iy. So we started with x, and we complexify this x to z. So real Langevin becomes complex Langevin. So there is an associated distribution p x comma y in the complex plane. We introduced the y variable, which is a new variable now. So we have x and y, and there is a combined distribution. And complex Langevin process, it finds this particular distribution. And the important sampling is not needed. Okay. So now we want to simulate this, so we can discretize the Langevin equation. Okay, so we have the real part and the imaginary part. So let's discretize this stochastic equation. Here epsilon is the step size. So this is the first order Euler discretization. And this case are the drift terms, okay, which are nothing but the gradient of the action, okay, real and imaginary parts. And we have a noise. We are giving noise only for the real part. We could also give noise for the imaginary part as well, but it will give the same physics. Okay, so it's usually people give noise to the real part. So the noise satisfies this constraint. Let's adapt this concept to field theory. Okay, so Parisi and Wu and Clowder in '83, they applied this method, this idea, to quantum field theory in pathological formalism. So Langevin dynamics, it happens in the fifth time direction. Okay, so we need to introduce an additional parameter or a time direction, and this is called Langevin time. Okay, it is a fictitious time. So the evolution, the dynamics is happening only in this direction. So we have a gradient of the field. Is the time derivative of the field is negative of the gradient of the action plus the noise time. Now the Gaussian, the noise is Gaussian, and it satisfies these properties, these constraints. So let's consider an arbitrary operator which is made out of the fields, the microscopic degrees of freedom of the theory. So we can define a noise average expectation value, which is given by this. Okay, so this observable, which is made out of phi, and phi happens at a given Langevin time, and we take the expectation value with respect to this noise, and it has this form. Okay, so there is a probability distribution for phi. So this phi is selected with this particular weight. So this probability distribution P of phi, it satisfies Fokker-Planck equation, which is given by this. Okay, so d by dt of phi of P, it obeys this particular equation. So for when action is real, so here is the action, we can show that in the limit Langevin time going to infinity, large Langevin time, stationary solution of Fokker-Planck equation, which is given by this exponentially of minus s, it will be reached. Okay, so we can show that for real action, but complex action, there is no such proof. So generating, so this, the tau going to infinity limit, it guarantees the convergence of Langevin dynamics. So it converges to the saddle points of the action and it stays there. It finds the correct equilibrium distribution. For complex actions, there is no such proof. Okay, we cannot show that. I mean, not yet. But we can identify if convergence works or not. Okay, so there are certain tools we can make use of, or diagnostics we can make use of that to identify whether it works or not. So here is a sketch. This is a simulation result from this paper, our paper. Arpit is my student. So here, this is for a theory. It has a scalar field, and we start with some arbitrary initial condition, and we let it evolve in Langevin time. So slowly, it is finding the equilibrium distribution. So it finds the equilibrium distribution, and it stays there. Okay. So once it stays there, we can start taking measurements. So let's apply this to some simple models. Okay, so models with supersymmetry. So this is work done with Arpit Kumar. Arpit is my PhD student at IISER Mohali. So we have one paper out, and another paper is in preparation. It's almost done. So let's apply this to supersymmetric quantum mechanics. Okay. So the question is, there can be supersymmetric quantum mechanics with complex superpotentials. Okay, so that means the action is complex. So we can ask whether there is a dynamical supersymmetry breaking in the system. Okay, we can ask this question. So Monte Carlo clearly fails because action is complex, and we can apply Langevin, complex Langevin, and see if there is supersymmetry breaking in the system. So let's consider a theory with complex action in one dimension. Okay, it's a quantum mechanics. So the degrees of freedom are, there is one scalar field and two fermions, psi and psi bar. We also introduce an auxiliary field B, which is made out of phi, essentially. The Lagrangian is offshell. So the action, it has this particular form. Okay. So dot is the time derivative, and W is a function of phi, and it is called the superpotential. So there is a W double prime, which is the double derivative of W with respect to phi, and then psi bar and psi. So there is a fermionic term appearing here, and there are two bosonic terms. Okay, so this is a form of the action, and this is Euclidean action, and we put it on a circle, okay, of circumference beta. So this action, it has a symmetry, this particular action, and this symmetry is known as supersymmetry. Okay, so for this particular action, there are two supersymmetric charges corresponding to the symmetry, and the action is invariant under these supersymmetric charges. So we can show that Q acting on S is 0 and Q bar acting on S is 0. So in the path integral formalism, we can write the partition function in this way. Okay. Now we want to study this theory non-perturbatively for an arbitrary superpotential. Okay. And our goal is to check whether there is dynamical supersymmetry breaking in the system. So let's put this on a lattice and simulate. And we will use complex Langevin dynamics. So here is our 1D lattice. Okay, the lattice has a finite circumference beta, which is T times A. A is the lattice spacing, T is the number of sides. Then we know that continuous derivatives, they have to become finite difference operators on the lattice. So the action of our lattice theory, it is this. Okay, so it takes this particular form. I am not giving the details. So once we discretize, it takes this particular form. So here, this del IJS is a symmetric difference operator, and this omega prime and omega double prime, these are the terms that contain superpotential and also the Wilson mass parameter. Okay, so we are using the Wilson discretization for this, for the fermions. So this action respects only one supercharge. The other one, Q bar, is broken on the lattice. So this action is invariant under supersymmetry charge Q. So when supersymmetry is broken, the partition function vanishes. Okay, so Witten showed this in his paper in 1981. So partition function vanishes when SUS is broken. So that means expectation values of observables normalized by partition function could be ill-defined. Okay, so that means we are dividing by 0. So we need to overcome this difficulty. So what we can do is we can apply something called twisted boundary conditions. Okay, so this appears in Lattice QCD as well. We impose twisted boundary conditions. So what we do is we apply periodic boundary conditions for bosons and twisted boundary conditions for fermions. So we introduce a twist parameter alpha. So introducing twisted boundary conditions is the same as turning on an external field in the system. So the twisted boundary conditions, they look like this. For bosons, it is unchanged. Okay, at site 0 and site t, it is the same. And for fermions at site 0, it is related to site t by a phase. Okay, e power I alpha. So,
sorry, Anosh.
Yes.
Sorry, a naive question.
Ah.
This supersymmetry, when supersymmetry is broken, some particular type of breaking is required for Z to vanish?
It's a general statement. It doesn't say what type of breaking it is. So I don't clearly understand your question. So there can be, I mean, we can break SUSY by introducing a mass term, for example. Okay. But there are theories where SUSY is broken dynamically. So we need to probe the theory using non-perturbative methods to see whether SUSY is broken or not.
So
By
if
looking at
SUSY
the
is broken dynamically, then Z vanishes. That is the statement.
uh, mm, that is certainly true. So now I'm wondering whether if you put in some term by hand, whether is it vanishes or not. That I don't know. Let me get back to you on that. So for dynamical SUSY breaking, is it vanishes when it is broken. Yeah. Okay. So we introduce this twisted boundary conditions for fermions. Then the partition function, it takes this form. Okay. So here alpha is the twist parameter, and we eventually we take the limit z goes to 0. Okay, we introduce this twist parameter just to make partition function well behaved. Okay, that is only usefulness of this. So it's like a regulator. So expect
quick
yeah.
question, Anosh,
Yes.
Sarindu here. This question is also bothering me. When does Z vanish? If you don't mind, could you update your slide and put that reference there so that we can take a look at it later?
Yes, of course, of course. So yeah, I will do that. Huh? Okay.
Yeah, thanks.
I mean, since Sorindu, you also asked this, let me tell you what is bothering me. I mean, normally one is more used to the kind of arguments where when supersymmetry is exact, then something is vanishing. I mean, somehow it's, so let's say I put some parameter which makes it
Maybe,
dynamically.
Shauman, if you don't mind,
Maybe,
you
yeah,
could let
maybe.
him go ahead and then have a discussion later.
Right, yeah.
Okay. So we define this the partition function with this alpha parameter in it. Okay. So we can construct an observable expectation value of an observable, which is defined in this way. So insert this O into the form of the partition function, then use the twisted action and take alpha going to 0 limit eventually. Okay, so we can compute observables this way. So we can also use mass gaps. We can extract mass gaps. This is the usual thing we do in lattice field theory. From correlators, we can extract mass gaps. We have bosonic and fermionic correlation functions. We can compute them on the lattice. Then we can extract using a Cauchy fit, or we can do a simple exponential fit over the first few data points for up to t/4 or something. So another observable is the field B itself, the auxiliary field. This field has no dynamics. It is made out of phi. So this field itself can be used to predict SUSY breaking. So if B is 0, SUSY is preserved. If B not equal to 0, it is broken. So that is another parameter. Then we can also use bosonic action on the lattice. Okay, so this is a form of the bosonic action. So again, I am not giving the details of the discretization and things like that. So we are using symmetric. So here it's the backward derivative. Then this is related to the superpotential of the continuum theory. So what we expect is the bosonic action should give 1/2 the number of sides. Okay. So if you measure bosonic action, if you get it as 1/2 of t, SUSY is preserved. If it deviates away from that, SUSY is broken. Okay. This is another tool. And another interesting tool is word identities. Okay. So we can so how can we get word identities from our action? So let's add source terms j theta theta bar in this way, and the q variation of this z, it should give 0. Okay, that would give us some constraints. And we are interested in we are looking at a particular type of word identity, this one. So there are several word identities, and we are focusing on one of them. Okay, and this word identity is obtained in this way. Take the second derivative of z with respect to j and theta, then q variation of it should be 0. And once we simplify all this, we get something like this, okay? A constraint among fields, and here ni is this. So on the lattice, we can compute this term, the first term, and also we can compute the second term separately, and we can add them up, and we should get 0, okay? If SUSY is preserved. So we can use this also to check SUSY breaking. Now let's look at some simple models. So we can look at double well potential. Okay, superpotential becomes something like a double well, and we will use real double well and also complex double well. Okay, since we are using complex Langevin, we should also study the complex action. So when we have a double well superpotential, supersymmetry is broken in this model. Okay, so it is discussed in Witten's paper in 1981. So Savrindu, this is the paper I was referring to. So I will put it there as well.
Okay, so, fine. Thanks. No, that's enough.
So SUSY is broken when supersymmetry, the superpotential is this form. So we consider a complexified version of this. Okay, just make G I times G. Okay, and we can use complex Langevin and check whether SUSY is broken or not in this model. Okay, and we can also use complex Langevin to study this theory. So let's look at some simulation data. So here, this is for the complex, this is for the real double well potential. Okay. So on the left-hand side, we have the Langevin time history of B, the auxiliary field. And we see that its imaginary part is non-zero, okay, and real part is almost 0. Then the expectation value of the bosonic action, we should expect this to be, it's on a lattice with 8 sides. So we should expect this to fluctuate around 4, okay, if SUSY is preserved, but it is fluctuating around, I don't know, 70 or something, 75 or something. So SUSY is broken in this model according to this diagnostic. Let's look at the complex double well potential. Okay, so here what we see is the B is fluctuating around 0. Okay, both of them. So indicating that SUSY is preserved in this model. Then the expectation value of the bosonic action, it fluctuates around 4. Okay, on T equal to 8 lattice, 8 side. So it fluctuates around 4. Okay, so again telling us that SUSY is preserved in this model. Then we can look at word identities again. So this is the real double well, and this is a complex double well. So for real double well, what we see is the word identities, instead of 0, it is fluctuating around some non-zero value. And for the complex action, it is fluctuating around 0. Okay, so SUSY is preserved in this model according to the word identities. So we applied several measurements, several types of measurements, and we are consistently getting the same type of result. Now let's move on to models with PT symmetry. Okay, P is for parity, T is for time reversal symmetry. So PT symmetric models, so it plays a role in Higgs physics. So we can apply this to
just a question. So the real double well did not have any phase problem, and the complex double well had, is it?
Real double well did not have any phase problem.
Achha. Yeah. So you did like normal Langevin dynamics for that and complex?
No. We applied complex for all of them. Complex works in normal cases as well.
Okay.
Yeah. PT symmetry, it plays a role in Higgs physics, okay, in 4-dimension theories. So if we impose PT symmetric boundary conditions for the Higgs part, so we can get the spectrum real and bounded from below. Okay, so in that way, it is promising. It is interesting. So we are looking at some lower dimensional models, supersymmetric models with the PT symmetry, and we ask whether when P is broken in this model, whether it induces Susy breaking or not. Okay, we can ask this question. And the PT symmetric superpotential it has this form, and it's given in it was explored in this paper, okay, by Bender. So here delta is a continuous parameter and G is the coupling. So let's use this as a superpotential and check whether Susy is broken or preserved. So Bender did the analysis for using delta, using perturbative expansion. Okay, he took small delta and he did the analysis, and it showed that Susy is unbroken in these models. Okay, so Susy is preserved. So now we can put in delta by hand in our simulations, and we can do complex Langevin and check whether Susy is broken or preserved. So let's explore Susy breaking in this model using a complex Langevin method. So path integral Monte Carlo fails here because action is complex in general. So here we studied a model with delta equal to 2, and here on the top row, and on the bottom row we have delta equal to 3. Okay, so what we get is Susy is preserved in this model. Okay, so the indication is that Susy is not broken, which is in agreement with what Bender has done. So here B fluctuates around 0 if you take the average. Then S alpha, it is T over 2, where T equal to 8 sides. So delta equal to 2 and 3. So we also looked at wide identities. So they are matching exactly 0. Okay. So here we can separate real and imaginary parts. So the real part, it grows like this, and the on one side, so the wide identity has 2 terms, and they should add up to 0. So if you look at separately, we see that the data, it goes like this and goes like this. Okay, and when we add them up, we get 0. So for delta equal to 2, delta equal to 3, we see that it's preserved. So we have data for other delta values as well. So that is, we are still collecting everything. So it seems like our simulations indicate that Susy is preserved in these models. So this model is in one dimension. Okay, it is quantum mechanics with the PT symmetry. So in our paper, which is already published, we did this for 0 dimensions, and we got the same result, saying that Susy is preserved for a given value of delta in this model. So our next study is to perform the analysis for 2-dimensional systems, and Bender did calculations for the 2-dimensional theory. So we want to do the same theory non-perturbatively, okay, for any value of delta. So we are focusing on that at the moment. So far promising, it looks promising. Now, how do we know that complex Langevin method is correct? Okay, how do we know? How do we check the reliability of this? So we can mainly use 2 conditions. Okay, correctness criteria. One is we can use Fokker-Planck equation, and the other is we can check the decay of the drift term. Okay. So Fokker-Planck equation, this was proposed by Gert Arts and others. The decay of the drift term, it was mostly proposed by Jun Nishimura and collaborators. So we can check this in our simulations and see if we can check if the simulations are reliable or not. So Fokker-Planck equation, what we can do is we can apply this operator, the Langevin operator. Okay, so take an observable O, and so at large tau, this LK on O, it should be 0. Okay, so here the operator LK is given by this. So once the equilibrium distribution is reached in our simulations, we should get LK on O fluctuating around 0. Okay, so this can be used as a correctness criterion for the complex Langevin method. So what we did is we took auxiliary field as the observable, and we studied it, applied L on this auxiliary field, and we checked whether it's fluctuating around 0. So what we found is L actually fluctuates, L times B actually fluctuates around 0. Okay. So this is for delta equal to 3, and this is for delta equal to 4. So I mean, this is indicating that, you know, things are not running away to infinity or anything. So it's reliable, okay? So this is what this is indicating. Then another test is decay of the drift terms, okay? So the drift term is the gradient of the action, okay, with respect to the field. And we define a quantity, something like this, okay? And we look at the probability distribution of U, which is the magnitude of, related to the magnitude of the drift term. So this probability distribution, it should be suppressed exponentially at larger magnitudes in order to guarantee the correctness of complex Langevin method. So Jun Nishimura and collaborators, they proposed this. So we studied that for our models, delta equal to 3. So here delta equal to 2, yeah. So what we see is it is actually going down, okay? So it is, so these two, these are going higher than exponential. But here we are, you know, seeing some kind of power law behavior, okay? So it also depends on the parameters of the model as well. So we have done this in smaller lattice sites. Maybe we should go to higher lattice sites and things like that. So some investigations are needed, but crazy things are not happening, okay? So they are all falling down, the decay of the drift term. So that is also giving us some confidence. So now let me move on to the work I did with Pallab Basu and Kasi Jaswin. This is a complex unitary matrix model. Okay, so this is more relevant for QCD with finite chemical potential. So this work has been published here. So a unitary matrix model, it appears in the one loop formalism of QCD on compact spaces. Okay, so we compactify QCD on S3 cross S1. Okay, S3 is for space, S1 is for time. And this is analogous to SUN gauge theories. So large N gauge theories, these type of compactifications appear. So this model was originally derived by these people, Sundborg, Ahroni, Alvarez Gomez, in various years. And they put various matter fields into this and studied this theory analytically, okay? And they came up with some nice results. So the question is, this model is complex. So can we apply complex Langevin for this model and reproduce the results, you know, people got? So the one loop effective action on this compact manifold, it takes this particular form. So here n running from 1 to infinity. So there is a partition function bosonic. Then this is a gluonic operator, double trace. Then there is a fermionic contribution. So this is a structure of the action. So here R is a radius of S3, and it has enough number of flavors of fermions in fundamental representation. So this model has a tower of quark energy levels due to the compactification.
Sorry, Anosh. Sorry, another naive question.
Yes.
So on your starting theory. So from the S1 side, you put phase factor for fermions at the boundary. For the S3 compactification, what do you do? So all the gauge fields, I understand.
I believe it is periodic. So beta is the inverse temperature. Okay, so here beta is inverse.
So S3 fermions are periodic. So all the fermions at the boundary are identified.
But the model has something similar to temperature. Okay.
That's the S1.
So
I was asking, what is the boundary condition for the S3? I mean, how do you make it?
S3 is periodic.
Okay.
S3 is periodic.
Okay.
So this model has a chemical potential mu. Okay, and mu can be negative or positive. So the action is complex. So the quadratic term in Polyakov loop, these are the contribution from the gluons, the adjoint fields. And then the linear term, these are the contribution from the matter fields, which are fermions in fundamental representation. So we can study this theory in the low temperature limit, which is beta going to 0. Then the gluonic contribution, it goes to 0. It is negligible. So we can write the action in this way. Okay, the fermionic action plus the van der Monde piece of the action. So then the action takes this particular form. Okay, this was derived in those papers I mentioned. So there is a tower again going through infinity, and there is a logarithm, and we sum over this logarithm. Okay, sigma L is defined this way, epsilon L. These are some energy levels, and they are defined in this way. Now, what are the observables of this theory? So it has Polyakov loop and its inverse, P and P inverse. So we can use this to study confined or deconfined phases of the theory. then fermion number, which is coming from the partition function in this way. Then we have quark number susceptibility, which is obtained from the fermion number. Then we have pressure, which is again coming from partition function. Here V3 is the spatial volume. Then from this, we can construct energy from pressure and the fermion number in this way. So these are the observables of the theory. Let's focus on a particular case of this model, which is called the single level model. Okay, so it has only one, we are looking at only one level, okay, one energy level. It is a truncation of the model. So only contribution from a single level survives in this model. So let's define a transition parameter, which is this exponential of beta times mu minus epsilon L. And we vary this transition parameter and we look for phases in the theory, confined and deconfined phases. So the action takes this particular form, okay, in this single level model. So there is no summation over L or anything, only sigma and U, and psi is a transition parameter. So we will vary psi and study the phase structure. So the effective action on the complexified angle variables, it includes a van der Monde piece and a Lagrange multiplier. So this Lagrange multiplier imposes the SUN constraint, okay. So the model, even though it is complex, it has this SUN constraint. So we look at the theta variables, the angles, which are coming from the Polyakov loop, okay, the diagonal elements of the Polyakov loop. So we are going from U to theta variables, and we get the gradient of the action like this. In the large limit, the integral over the angles, thetas, they are dominated by a saddle point, which is given by this. So this model has a sign problem, okay, in the presence of mu appears through this psi variable. So as a result, the saddle point configuration will lie out in the complex plane. Okay, it will no longer be on a unit circle. Okay, it will have some strange shape. So analytical study was done here by Simon Hans paper in 2010 for this particular model, single level model. So we will do simulations and compare with what Simon Hans and others got in their paper. So we see excellent agreement. So let's look at small psi confined phase. So when psi is very small, the theory is in a confined phase. So the effective fermion number vanishes. We should get the fermion number equal to 0. And we can analytically show that these people, they have shown this, that Polyakov loop equal to 0 and P inverse is this non-zero number, okay? So P not equal to P inverse. It is a feature of the complex action, okay? So we can check whether we are getting exactly the same value, okay, in our simulations. Then as psi, the parameter is increased, the contour of eigenvalue distribution opens into an arc. So let me show some figures, simulation figures. So it starts with a closed distribution, okay? And as we increase psi, it changes, it deviates away from circular shape, and then it opens up, okay? It becomes an arc. Then again, the gap widens, then it becomes this, and again, it is going, it's trying to close, okay? So the gap closes and it closes. So it is going through a confined to a deconfined phase, and then again back to a confined phase, okay? So that is what is happening. So there is theory behind this, and these are the values that should happen, you know, for small psi, there is a confined phase. Then as the matrix model, so this model, it undergoes this Gross-Witten-Wadia transition, okay? So there is a third order phase transition in this model, and we can show that, okay? So there is a line of phase transition on the mu-T plane, which has approximated this value at low temperature. Then we can look at the large psi. Again, the fermion number is not 0, it is sigma, okay? For the small psi, it was 0. Now it became sigma, not 0. That means the level is now occupied, okay? And Polyakov line expectation value, P has this value, and P inverse is 0 now, okay? So previous case, we have P0 and P inverse is this. So the behavior of P and P inverse, it swaps over along the replacement, okay? Psi going to minus 1 over psi. Then the large psi confined phase, it persists until a psi critical value, which is given by this, okay? So for smaller psi values, the contour is not closed, and confined phase does not exist. Then there are points of transition, and they satisfy this constraint, psi1, psi2 equal to 1. And on the mu-t plane, we have this relationship, linear relationship along the for the phase boundary. So let's look at the region in the middle, which is the deconfined phase. So when the parameter psi is between psi1 and psi2, the two transition points, it goes through a Gauss-Witten-Wadia phase transition. Okay, so the eigenvalue distribution exhibits the shape of an open contour. So we get this particular condition, okay, which connects the parameter with the fermion number. So we can compute fermion number in this way. So this was derived in this paper by Simon Hans and collaborators. So we see that across the transitions, the fermion number and its first derivative, they are continuous. But the third derivative and or other higher derivatives, they are discontinuous. Okay, so that means there is a third order phase transition in the model. So this is similar to just as the original Gauss-Witten-Wadia model. Okay, and we look at a single winding of the Polyakov loop, and we should have P this expression and P inverse this expression. Okay, and we can check this whether we get this through our complex Langevin simulations. So we performed simulations, and we actually saw that transition where the model starts with a confined phase, then it goes through a deconfined phase, and again coming back to a confined phase as this parameter is increased. So this is an explanation of this figure and what we did, how many Langevin steps and things like that. This is for number of colors, number of fibers equal to 500 with quark mass m equal to 0. This is the fermion number. So it starts with 0 as we change psi, as we increase psi. It starts with 0, then slowly it increases, and the levels are filled, and it reaches this value, sigma, but I divided this by sigma so that it's 1. So here data are for n equal to 500 and n equal to 3. So these rectangles, these diamonds, they are n equal to 3, and the red is n equal to 500. And the analytical result is the solid curve. Okay, that's for n equal to infinity. So this is again explanation of this figure. So we can look at the Polyakov loop as we change this parameter. So it goes through
is this a requirement of going to this matrix model that n has to be equal to nf, or you just
no, just we can plug in any number. Okay, in simulation we can have
nf just comes as a overall factor outside, or how does nf come in the action?
Let me check. NF is part of the sigma, I think, in the definition. So let's go back. So sigma is NF over N, okay? So appears as the ratio.
Okay, right. Okay.
Okay, so let's look at the Polyakov loop and the inverse Polyakov loop. So again, this solid curve is the analytical result for n equal to infinity. Okay, the solid curve and the dashed curve, and we have data points for n equal to 3 and n equal to 500. Okay, so when n reaches 500, it is lying on top of the exact result. Okay, the analytical result, and for n equal to 3, it is slightly above. So this is an explanation of the figure. Now there is something called silver blaze problem. Okay, so we encountered this in actions with, complex actions, models with complex actions. So let's consider a particle with mass m and a conserved charge at a low temperature. Okay, so we can consider the chemical potential as the change in free energy when a particle carrying the conserved charge is added to the system. Okay, so that is the energy cost of adding one particle. Okay, change in free energy. If mu less than m, that means there is not enough energy available to create a particle. So that means there is no change in the ground state. If mu greater than m, then there is plenty of energy available. The ground state has non-zero density of particles. Okay, so can we see this through our simulations? That is the main question. So statistical mechanics, it tells us that at non-zero temperature, the density becomes non-zero at mu equal to mu critical equal to m. Okay, so this is the onset. Okay, where the density becomes non-zero. So at strictly zero temperature, we note that the thermodynamic quantities, free energy, pressure, fermion number, susceptibility, etc. They are independent of mu when mu less than mu critical. Okay. Now, as long as mu is below the mass of the lightest particle in the channel with appropriate quantum numbers. So now the question is how this independence emerges in numerical simulations. So it is a non-trivial question, and this is known as silver blaze problem. Okay, and in our model we actually see this silver blaze phenomenon. So for P and P inverse, we see that. So it's 0, starts with 0. Then the onset is around 25. Okay, and suddenly it jumps. Okay, so here also the fermion number, it is 0, and at the onset it suddenly jumps. So this is a silver blaze behavior, and we see this behavior in our model as well, which is interesting. So this is an explanation of this figure. Now let's look at QCD on S1 cross S3 at finite temperature. So we set n equal to 3, number of colors. So we can simulate the model for n equal to 3, and the action has this particular form. So here we simulated we looked at the data for fermion number as a function of the chemical potential. And we see that, so this is for n equal to 3 and this is for n equal to 30. Okay, these are numbers. We can plug in these numbers into the simulation code and get the data. So what we see is there are certain changes, say when mu equal to 1.5, 2.5, 3.5. Okay, there is some kind of level structure that is visible here. The presence of an occupation level structure that is evident in this. So transitions occur when the energy E minus mu, this quantity changes sign. Okay, so that is when mu passes through a quark energy level, these transitions occur, and we can use this Fn as an order parameter. Okay, for the phase to find the phase of the theory. So again, saying that third derivative is discontinuous. It is of Gross-Witten-Wadia type, the phase transition. So we can look at the Polyakov loop as well. This is for n equal to 3 and this is for n equal to 30. And again, we see that the transition happens at 1.5, 2.5, 3.5, etc. So this is a series of Gross-Witten-Wadia transitions. Okay, as we increase mu, it goes through confined, deconfined, confined, deconfined phases. Another feature is the width opens up. Okay, the width of this peak, they open up. Okay, so I guess that's it. So conclusions, complex Langevin, it sounds promising. It's a promising method to deal with complex actions. It works well for lower dimensional theories, okay, almost all of them. There are some exceptions. Then it can be used for models relevant for superstring theory and ADS-CFT. So Jun Nishimura has been working on this. So this is a BFSS model and IKKT model that are supposed to be supposed to contain superstring theory, and they take part in AD-CFT correspondence. So there, once we integrate over the fermions, the determinant is complex. Okay, so again, we have to be careful when we do Monte Carlo of this model. So Jun Nishimura has been looking at this using complex Langevin. Then the real test is QCD in 4 dimensions. Okay, QCD with finite baryon quark or quark chemical potential. So how can we simulate this? So this is again, there are several collaborations working on this. So the main problem is the running away problem of from SU3 to SLN, the general the non-compact group. Okay, so that is a problem. In the lattice QCD, what we do is we unitarize the link fields. Okay, occasionally, because there can be numerical errors. But here, that cannot work because it is not unitary. Okay, it is complex. It goes away. So we need to come up with some, some clever techniques. One of them is something called gauge cooling. Okay, so people are working, looking at these type of ideas. So this is the ultimate goal. Okay, so simulate QCD with finite chemical potential. Yeah. So that is it. Thank you. So I will take some questions.
Okay, thanks, Anush. Somen, go ahead.
So these Nishimura, these ADS-CFT works that you have mentioned,
yeah,
are in which dimensions are those?
So this Nishimura's work, his 2019 work, is Euclidean IKKT model. So it is in 0 dimension, space-time is a point. And there are 10 bosons. Gauge group is SUN. Sorry, these are SUN matrices. There are 10 bosons and 16 fermions. So this model is obtained from n equal to 4 superangles in 4 dimensions and compactified to 0 dimensions. Okay. So this model, the prediction is when it has a complex fermion determinant. And this determinant, the complex nature, it induces a spontaneous symmetry breaking in the system. So this, the scalars, they are invariant, supposed to be invariant under SO10 rotational symmetry. But this fermion determinant breaks that symmetry spontaneously to SO6 cross, SO7 cross SO3, okay? So that, somehow 3 is picked out, okay? So, and his claim is that is why we have large 3 spatial directions. And there are observables that can monitor, how things, separate and things like that.
Okay, thanks.
Yeah.
Yeah, so Debashish, go ahead.
Hi, Anosh.
Hi,
this is
Debashish.
Debashish. Yeah, thanks for the nice overview and the talk.
Yeah, sure.
Actually, if I could make a comment, so if you could you please go back to a few slides where you were showing like the gross, what you call the gross Fourier-Witten transitions, exactly those. Yeah, this figure with the fermion number.
Oh, by the way,
Exactly.
the Bashish, you and Shailesh Chandrasekharan, you guys have done some nice work back in the days. And there also this type of structure is evident.
Exactly. So I just wanted to point out one interesting thing I noticed. So in your figure, I see that these transitions happen at very regular intervals of mu. There's 1.5, 2.5, 3.5. So I was wondering, like, if you now try to subtract the energies of putting 1 particle, 2 particle, 3 particle, you probably get the binding energies of the n particles.
Okay.
Systems. So, you'd also have some information about the, like, if 3 particles are forming a bound state or 2 particles forming a bound state or so on. So, yeah, I mean, looking at this, so looking at the regular structure, exactly. But, like looking at the regular structure, I somehow have the impression that it doesn't cost any extra energy to put 2 particles or 3 particles. So, I don't know. I was just wondering, are they really free or are they weakly interacting as you increase the chemical?
That is a good question. I don't know the answer to that. That is something to figure out.
Yeah, I think you could have more information about the nature of these states.
Right. Yeah, whether there are bound states in the model.
Exactly.
Yeah.
Right.
Yeah, that would be interesting. Yeah.
Right. And the second thing is that, like at some point, like when you were looking at all these different 1D systems, right? This one with the complex these quantum mechanical models. Right at the beginning.
Models.
Right.
Yes.
And you were also had this PT symmetric models and so on.
Yeah.
So you were saying that you wanted to see if the ground state breaks supersymmetry. So is there any kind of conventional wisdom like you expect, like for given some kinds of superpotentials, you expect the supersymmetry to break in the ground state, or is there?
The conventional wisdom we have is Witten's paper, okay, from 1981,
Okay.
but that is for polynomial potentials, okay. So it is for the highest power of the polynomial is even or odd. In one case it is broke, and the other case it's not. So that is the thing I can think of. Then for general polynomial superpotentials, okay. But when say the superpotential takes some other form, like I don't know, some cosine of something, things like that, then I don't know. Maybe there may be some other tools to explore this, but I don't know. So in this particular model, there is no such tool. Okay, this particular potential, one has to do some kind of perturbative or non-perturbative, calculations.
Right. Okay, thanks. Thanks also for the talk. That's very nice.
Actually, Anosh, I had questions might be similar to Debashish's. So if you go to the partition function you wrote for the S1 cross S3,
which partition?
So I think a little bit ahead. So where you went for the single, maybe if you go a bit back, So this seems like, Yeah, this seems very much like independent particles, right? So you have a for every L you have some sort of a energy level, and then you just do the log. I mean, it, oh, I see.
Log of the product of two
Exactly, that's right.
determinants.
But I guess because of the U, it's yeah, okay.
There is U and U inverse.
Yeah.
Yeah, and U times U inverse is yeah. So U not equal to U inverse. Okay. So yeah.
Okay. Now it's clear. Okay.
Yeah.
Hi, Anosh. This is Nilmani. Can you hear me?
Hi, Nilmani. Yes.
Hi.
Yeah,
Yeah.
I can. Hi.
Yeah. So my question was, so in your supersymmetric, that quantum mechanical example that you have given, I believe those can also be done through thimbles. Has anybody done it?
Yeah, of course. Yeah. One can do this through thimbles. Yes.
And I just want to compare the results. I mean, you're compared to there.
So we are thinking about this. So we are thinking about doing the same analysis on left shift thimbles. So we have recently we put a paper with a master's student here, and this was looking at thimbles in some zero-dimensional systems. So we are trying to go to higher dimensions, 1D quantum mechanics. So it would be interesting if we can compare the results through the two methods.
Okay.
So in this zero-dimensional theory, were the results known using other tools, or these are the first results?
These are the first results. I mean, yeah.
Okay.
So for the real superpotential, it is known, but complex, no, I don't think so. Yeah.
And for
but
this,
as I mentioned, for PT symmetric, it is known.
But only for small delta, right?
Only for small delta. Yeah.
And then you extend it to the non-perturbative regime.
Exactly. Okay. Yeah.
Okay, are there any further questions? Okay, it doesn't look like. So in that case, let's thank the speakers.
Thank you.
And hopefully see you sometime soon.
Sure. Yeah. Thank you so much.
Yeah.
Okay. All right. Yeah.
All right.
Thanks. Yeah. Bye.
Bye.